Okay, good morning. Greetings to intermediate algebra students. I'm going to work through some stuff today. We have two kinds of equations going on right now, and that's where I want to get started. Simplifying radicals is also on the agenda for this week, but the two kinds of equations I want to kind of compare what goes on there and make the emphasis on the part that gets a little tricky with each of these. So I wanted to spend some time on that, and then of course questions that come up if you have any on the lab that you want to see worked through, or questions from the homework. I have access to these right here. So if you have some questions from there, drop them in as we go along. I'm going to start with the equations and try to emphasize the catch to this. So let me get set up for that. So equations that have a square root in them, and equations that have a squared with them. These are kind of two sides of the coin. They're out of two separate chapters now, but it's the connection between these two that I want to make while we have some time here to work some examples on it. These kind of undo each other, right? These two operations, the square root and squaring, and we have to be careful which one we're talking about. But the square root is the radical and the squared is the exponent. And these kind of undo each other in the sense that 4 squared is 16, and the square root of 16 is 4. So we get back where we started from, right? If we're only talking about positive numbers, then these two undo each other perfectly well, and all is great. But these are equations. We're not always talking about just positive numbers, so things get a little bit more complicated, right? You can also start with negative 4 squared. That also comes out to 16. The square root of 16 is still just 4, so that's not going to undo each other perfectly there. And that kind of difference, because we're not talking about a one-to-one function, that kind of difference means we have to be a little careful at a couple of steps on this thing. So I want to kind of compare these side by side of what we do on this, and make the comparison here and see where that that factor comes into it. That possibility comes into it. So I'm going to start with one from the lab. Just this is a good example to start with. I'm trying to keep things simple with our equations with radicals. We're not going to get complicated about it. But here's an equation that has a square root in it. Our regular equation solving thought process is I want to try to get get rid of the most complicated thing, and that radical is the most complicated thing. Oh yeah, well, okay. We had a question come in about negatives. That is a possibility we're going to have to deal with here, that we might get a negative inside of the radical when we're doing this also. So I want to think about those some today also. That's kind of another side of this that we'll get to. I'll get to some examples on that also. But using these things to get rid of each other is the main idea. I have square root right here. That's the thing that I'd like to get rid of, the most complicated thing. I can get rid of that by squaring, but I have to have it by itself here. You can only square both sides of an equation. You can't like distribute that and square little pieces. It doesn't work that way. You can square both sides of the equation, but I got to have this as one side of the equation. I got to get rid of the 5 first. So I'm basically going to rearrange things as the first step to get that radical by itself. Those aren't like terms, so I get 2 terms over here. That's going to be important. So that's the one step that you can take. It's called the, well, really is multiplying both sides by the same thing. If these are equal, then we can square both of them. We're really multiplying by the same thing. So we can do this to both sides, and that gets rid of the radical here. careful with this. This is x minus 5 multiplied by itself. I have two terms there. I'm going to have to multiply that out, right? That's a little bigger than it looks. I got to FOIL that thing out or expand that. So I'm going to get a polynomial thing here. But I have an equation now without radical in it. It's just the kind of equation that we were dealing with zero factor property. I have an x squared term and an x term. I'm hoping I can factor something. So rearrange that a little bit. Or get to 0 on one side. I'm going to do 0 factor property on this now. So it turns it into an equation without a radical. Then I can get a 0 on one side if I subtract x. That's going to make that a negative 11x. And subtract 7, that's going to make that an 18. So when I move everything to one side, that's the form I got. If I'm able to factor it, I can solve it out that way. So I'm hoping this factors, and sure enough, it does. A couple of nice factors from that. Property says either x minus 2 is 0 or x minus 9 is 0. Now, you don't necessarily get something this complicated when you do this. Squaring both sides, you don't know what you're going to end up with here. Sometimes you get a thing that needs to be factored. Sometimes you get an even simpler equation, but it gets rid of the radical. But you can make false stuff into true by squaring both sides. That's kind of one of the impacts of this idea here, is that this is false. But when I square both sides of it, I get 16 equals 16. It ends up true. So when we square both sides, sometimes things end up true that aren't really true in the original. That's why we got to check our solutions from this to see if they really work. The solutions that I got here, this is 0 when x is 2, and this is 0 when x is 9. So I have two things that look like solutions. But if you go back to the original with x equals 2, it doesn't actually work. When x is 2, I have square root of 9 here, which is 3 plus 5 is 8. That's not equal to 2. That's not the right value there. So that one doesn't actually work in the original. And that'll happen a lot. Because I squared both sides, sometimes I get something false. It looks like it ought to be true in the end, but it doesn't actually work. So I'm getting rid of that one. X equals 2 does not work. Got to check the other one separately. 9, if I come back to the original with 9, I get square root of 16, which is 4, plus 5 equals 9. X is 9. I get 9 equals 9. That works out right. So the 9 does check. Kind of have to check these individually and see what happens. But the x equals 9 is good. So I didn't do any steps wrong. I did exactly the right algebra all the way through this. But you get what's called an extraneous solution. And that just doesn't actually work in the original because of that step of squaring both sides. We got to be on the lookout for that. For any of those that started with a radical, you'll get answers by a process like this, but then you have to check and see if they actually work. Now, you should also realize if I had something other than numbers that worked out nice to factor right here, this wouldn't really help me if I got something that didn't factor. We still have this big question out in front of us of what happens if you get to something like this and your polynomial is prime and doesn't factor. What are we going to do? We still have to deal with that situation. We're going to deal with that. Come on, we're building up to that type of quadratic. That's the one topic we still have to do this semester. Really. And these tools are leading up to it. So hang in there and roll up. For now, the problems that they've selected for this chapter are all carefully selected so that you'll be able to solve them either as a linear or as a zero factor property thing. Now, comparison. I am going to get to square root of a negative, but that shows up more on this kind of problem. So comparing this was an equation with a radical. What if you have an equation with a squared? And I'm going to start with, this is also one from the lab, but I hope people got okay. X squared minus 169 equals 0. And it says to solve this on the lab using the square root property. So this is an equation with something squared in it, and I can use the square root to get rid of that, but I have to use that square root property. Now, you might be thinking, this is a difference of squares, and I can solve this by the zero factor property. And you'd be right on that. This is going to factor this one. Because 169 is 13 squared, I get nice factors, and I'd get nice solutions from that. X equals 13 or x equals negative 13 are both going to work there. Those are the solutions to this, but that's not using the square root property. That's using the zero factor property. I want to see what happens with the square root property. What I have in common with this thing over here is you have to isolate this. Just like I squared both sides after I got the radical by itself, I can square root both sides, but I got to get the squared thing by itself. So for the square root property, I'm going to move everything to this side so that I have the squared thing by itself, and then apply this square root property. And the square root of 169 is 13. So here's the tricky part on this kind of thing, is that I get a number out of this, but really this number or its opposite would both work. Obviously in that equation, this could be either one. So when I take the square root of both sides like this, I'm really talking about plus or minus 13. Both of those solutions are going to work here. The deal with this, the square root of 169 is just 13, but the square root of x squared is really the absolute value of x. This thing, the absolute value of x has to be 13, and that means x can be either positive or negative 13. Those are both going to work right here. So that's where this kind of situation comes in when you're using the square root of both sides. Anytime you take the square root of both sides of the equation, you're going to have to write that plus or minus in there because both of those possibilities are going to work in the original. Now, the nice thing about this is it doesn't have to factor. This one could have been done by factoring because that was a nice number right there. But what if I have x squared minus 160 equals 0? That's not a perfect square anymore. So I can't factor it into x minus something and x plus something. It doesn't factor. But I can still do it by the square root property. I just don't get nice numbers out of it. Square root property says I get the squared thing by itself. And then I take the square root of both sides. And remember my plus or minus there, and I get x equals plus or minus the square root of 160. Now, when that doesn't come out to a nice number, that's when we use our simplifying radicals. So this is where the simplifying radicals comes in. I'm stuck with a radical because it's not a perfect square, but I want to write it simplified as much as possible. I want to shrink that radical as much as possible. And this is 16 times 10. So there is a perfect square factor. So I can write this as plus or minus 4 radical 10. That's a little nicer form of the answer right there. That's the deal. Now, square root of a negative number thing is going to show up sometimes in this. I'm just messing with the same equation a little bit. I want to do a couple of more very similar to this and then see what happens where that square root of a negative would show up. So I'm starting with simple equations like this. If I have x squared minus 5 equals 0, I can still solve it by the square root property. I isolate the squared thing. Take the square root of both sides and remember my plus or minus when I do that. That's your square root property. That might not simplify at all. If you just get a 5, it's not a perfect square. It doesn't have any perfect square factors. So that one doesn't simplify at all. That's it. Now, one more along those same lines. What if I'm starting with x squared plus 5 equals 0? If I just push through these same steps here, I can still get x squared by itself. I can write square root on both sides and remember my plus or minus there. X is plus or minus the square root of negative 5. Looks great. but should recognize that's not a real number. If I took any kind of number and squared it, that result would be positive. And I add 5 to it, I'm not going to come out with 0. This is not true for any real number because this is already going to be at least 0. If I add 5 to it, it's not coming out to 0. It's never going to happen for real numbers. But this is still a solution. It's just a non-real solution. So we haven't dealt a lot with those, but I'm going to separate this out using the I thing. So anytime I have a negative number, that's just -1 times 5. That's what that symbol means, is multiplied by -1. So if I separate this piece out, I can just get a regular square root of a real positive number there. This thing is what we call the imaginary unit I. So for that sort of thing, I'm going to call that I square root of 5, and that's a complex number. It's a imaginary number now. So the I is the imaginary unit for that. Anytime square root of a negative shows up, you can separate out the -1 part, and the square root of that becomes I. So you write this is I square root of 5. This is just the number, 2 point something that you could get from that. But it's multiplied by I in this thing. And that's your imaginary units, the square root of -1. There's a whole study of mathematics that deals with what happens once you have I mixed in with the real numbers and you get complex numbers. And there's a whole bunch of cool things that happen there. We're not going too far down that road. But since I is the square root of -1, I squared is equal to -1. So if you have an I in your answer, it just stays there. But if you have an I squared, you can replace it with -1 and simplify things that way. So this is the facts to keep track of out there, but we're not going to, well, where that will happen is if you try to check your answers on this, right? My answers are I square root of 5 and -I square root of 5. And if I plug one of those in to check it into the original equation, I get I square root of 5 squared plus 5 equals 0. And that's I squared times 5 plus 5 equals 0. And that's where I have to remember this. I squared is just -1. That's -5 plus 5. Sure enough, that equals 0. Yeah, that comes out great. So that's where one of the places that would show up. So it's true that there's no real solution to this equation. None of the real numbers would make this true. But these two imaginary numbers make the thing true. There's still solutions to the equation. They're just not in the real number system. Your number line has a 0, and it has positive and negative real numbers. These aren't on the number line. These are in a different number system entirely, which you could spend whole semesters looking at what happens in that cool number system over there. And I have, but you're probably never going to do that. So you want to see them as solutions to equations. If you're going into electrical field, you're going to use imaginary numbers to model stuff because it works really well for that. And the rest of you probably aren't going to see that much more about them. So we're just going to do them as they'll show up in the solutions to this kind of equation sometimes. I'm not going to spend much time on it. When you take the square root of both sides, if the thing that's in here is negative, then you've got imaginary solutions instead of real ones. And simplifying the radical means writing that as I square root of the positive part. That'll show up. I don't think I did any of those on the lab this week, but we will see them as we go along. Now, key step to all of this was being able to do this right here and get the squared thing by itself. Before you can take the square root of both sides, you have to have this perfect square thing isolated. And that's only going to work for certain kinds of equations where you have a squared thing and no other x's going around. That's what we're dealing with now, is this kind of equation. We should recognize this is limited to a certain class of equations where there's just a perfect square thing that you can isolate. It might take a little work to isolate it. Let me do another one off from the lab, just as another example on that. It starts off as -2 k squared plus 8 equals 0. It says use the square root property to solve the equation. So I can't take the square root of anything. Well, I could take the square root now, but that would be a big mess. I want to isolate the squared thing first. So I want to get this piece right here by itself. I got to get rid of the other stuff. So regular order of operations and stuff, I'm going to get rid of the 8. I'm not using the 0 on the other side. I'm not using that property. So let's isolate the squared piece. Now I got to get rid of the -2. Division. That gets the k squared by itself. That comes out 4 on this one. That's nice. Square root property. Yeah, I'm ready to do the square root of both sides now. So both of these things are about, remember your plus or minus when you do that. If it comes out to a nice perfect square, then you have nice number solutions. Simplify that radical. So that's your square root property. You get the squared thing by itself and take the square root. On the other hand, equations with radicals, you get the radical by itself and you square both sides. Both of them start off by isolating the thing and then applying this something to both sides that'll get rid of your complicated part. Now I'm going to lead into where we're going next with something where it's a little harder to isolate the perfect square part. There's a little mystery to it, and I want to plant the mystery out there before we answer it. Later on, I'm going to do some stuff Friday to answer the question of how this really works out nice. But if I start off with x squared minus, if I have an x term floating around also, that's going to make it awfully hard. I don't want to do that one. But if I have an x squared floating around also, an x squared and an x term, then being able to isolate that squared part is not gonna be easy to do. I want to do x squared minus 6x equals -5. I got some old stuff. So if you look at that and you think, oh, I should move it to one side and use the 0 factor property, well, you're right. That is what you should do on that. But I want to compare it to what we did over here. If I can get a perfect square thing on one side, get the squared thing by itself, then I could do this by square root property. But if I get x squared by itself, then I have a variable over here. This is no good, because if I do the square root of both sides now, and remember my plus or minus, I get this crazy looking expression here. That doesn't really help me. To say x is plus or minus the square root of 6x minus 5, well, I still don't know what x is. So that really doesn't help at all. We're going to go a very different direction on this, and it's going to look a little weird, but that's what I want to think about. The only way the square root property does any good is if I can get just a number in there. So I really need this to look like something squared by itself equals just a number over here. And the way to do that on this one is a little strange, but I'm going to add 9 to both sides. Instead of moving stuff to the other side, I'm going to add 9 to both sides. And I'm leaving that 9 as a little mysterious right now. There's a pattern to this that we'll look at. But if I do add 9 to both sides, I get x squared minus 6x plus 9 equals 4. And I set that up so that that's a nice perfect square. Now, if you think about the factors of x squared minus 6x plus 9, it factors into x minus 3, x minus 3. I made that into a perfect square thing so that I could get squared thing by itself, just a number on this side. Then my square root property will work from here. So this is very much like the first one on the lab, only they gave it to you in this form already, where it's a perfect square there, and you're ready to apply the square root property now. I got my perfect square by itself, square root of both of those. Remember the plus or minus, because that's how the property works. And you get x minus 3 equals plus or minus. This one came out nice again, 2. And then I can get x by itself. I have to add 3 to both sides to get x by itself now. So you got x equals 3 plus or minus 2. Now I know what 3 plus 2 is, and I know what 3 minus 2 is. So I get those two solutions out of that. That worked out nice for this one. But yeah, I'm being kind of vague and mysterious about where that 9 comes from. So that's the question. Why did I add 9 to both sides? There's no 9 in the problem. There's a pattern to that we have to pick up on. How do we make this into a perfect square if it doesn't start out that way? That's called completing the square. Yeah, you can add anything you want to both sides, but the number 9 worked here because it fit this pattern. So I'm going to dive more into this. You don't need it for this week's, at least the early stuff this week. I'm going to dive more into it in Friday's video, really digging through that process. But the deal is you need this to be that perfect square number, but not just the perfect square, but it has to fit with the 6 that's here also. To make that a perfect square, this number is just half of what we had right there. This number squared is what sits over here. So that's why 9 works on that one to make a perfect square. There's always going to be a number you can add, and we can figure it out by that same pattern. We're going to have to look at that. Negative 6 divided by 2 gives you negative 3. That's what I need to have in here because of how that foils out. And then negative 3 squared is 9. So that's what I have to add to both sides to get that perfect square form. We're going to really dig into that pattern because you can use that on more complicated equations. You can make stuff into a perfect square. That's what your completing the square pattern really is. It's making something into this form. Something squared, just a number on the other side. That's the deal. And that's when your square root property can work from there. Applications would be good for this. We're not going to dig into a lot of them in this class, but there's a ton of things that actually fit this kind of equation. These are quadratic equations, something that starts off with a squared term, and it's called quadratic because that's a term for square. Quadrilateral is like a square. So these kind of equations fit a lot of physical situations. Actually, if I have just quickly, and I don't think I put any of these word problems into there, but if I have area of something and these are both unknowns, but I've got some kind of relationship between them, like a W, and this one's supposed to be 2W plus 5 or something. We've seen these kind of rectangles before. We did perimeter stuff, but if you do area stuff on this, then you get one of these equations you have to solve. If your length and width are related and your area is supposed to be 112 square meters, and these are supposed to be related this way, then W times 2W plus 5 is equal to 112. And we do get something that has a squared term, a variable term, and a number term, like that quadratic situation. Finding the solution to that means we could set up a rectangle that's in this kind of form. We could deal with that. And then another completely unrelated thing is if you if you have gravity, this is the ground and there's gravity going on. If you launch a projectile up, it's going to follow this kind of path because of the way gravity works on it. It's going to follow that kind of a path, which ends up being a quadratic function. So you will work. If you take physics, a lot of you are going to have to take general physics. You'll see a ton of this stuff where they launch a cannonball or some other, baseball, any kind of object like that. If you just look at the effect of gravity on that, it fits this kind of gravity. It fits an equation that has a squared term and a number term in it also. Depending on the units you're using. So those also turn into this kind of equation if you want to see where this is at height, where it's 50 feet above the ground or where it hits the ground or any of those kind of questions. You end up solving that same kind of equation. So a lot of stuff in physics and geometric stuff that turns into this kind of equation. So we want to get the algebra part of it down so that as you go on to either Math 121 or general physics, you'll see the applications of it a bunch there. Also in business, I don't teach the business algebra, but there's same kind of equation comes out of doing revenue profit functions in business analysis. If you come up with a model that fits how your price works, you get this same kind of a curve there. So that's going to be next semester in some form for a lot of you. I want to get the algebra side of it down. And since we're taking the square root of a number in this, we do have some simplifying. We have to work through the simplifying stuff on that radical. So that's where simplifying basic radicals comes into it. We do another square root property problem with ugly numbers. Right? If I have x squared plus 5 equals 113. We have some simplifying radicals to do on that. I'm not ready to do the square root yet because I don't have my squared thing isolated. I got to get rid of the 5 first. I want perfect square and number over here. So this is a simple one. To do that, I just have to do the minus 5. And I get x squared equals 108. And then apply your square root property here. So the square root of x squared equals the square root of 108. Remember the plus or minus you get out of this when you call that x. This is plus or minus the square root of 108. And this is where we're going to use our simplifying stuff. If you want just a decimal answer, of course, you could do this. Your answers would be 10 point something and negative 10 point something. Great. But if you want to keep it exact, we can write it using simplifying radicals a little bit. We can shrink the radical. 108 is not a perfect square because the square root's 10 point something. Doesn't come out nice. But it's got a perfect square factor. This is divisible by 9. So I can separate out 9. This is 9 times 12. And I can simplify it that way. And then hopefully I'm asking myself, am I done here? Wait a minute. I still have a perfect square factor. 4 goes into this. So I can even go further with this. I got 4 times 3. I can break that up a little further. That's a 2. Square root of 4 is 2. So I got 3 times 2. 6 square root of 3. Right? I can shrink that all the way down to here. My answer would be plus or minus 6 square root of 3. And since we're working these things in, let me do a comparable one that doesn't end up real numbers like that. So another thing, no x term yet because I'm not dealing with that whole pattern, but we got a perfect square thing that we can pretty easily isolate, just adding 8 to both sides, but I might end up with a negative over here, and that's negative 19. And so if I apply the square root property, here's the step that's going on in my plus or minus in there. X is plus or minus. It's the square root of negative 19. Now, if you put that in the calculator, depending on what calculator mode you're in, you either get an error or you get something with an I on it. We're not really looking to do calculations with these things in the calculator. I'm just going to write it in exact form. But it's not a perfect square because it's negative. But I'm going to separate out the I part. Anytime I get square root of a negative, it's negative 1 times the number, and that's I. This is just I right here. So I'm just going to write this as plus or minus I radical 19. And that's the really the two solutions for that. I got to remember these represent two different things. X is I square root of 19, or X is negative I square root of 19. Both of those will work. Those are your solutions to that. Those end up involving the I in there ends up being a good model for what happens with alternating current when you have an amount, but you also have sort of a phase angle to it in alternating current or other wave equations. Those end up having nice applications out there also if you're in the electricals. Again, I'm not going to go into that this semester, but that's in the future for you if you're in electrical engineering tech or some of those fields. Okay. Now, rationalizing the denominator is the other thing I wanted to talk about. What if we get a fraction in one of these things? Leads to rationalizing the denominator. So one other type of thing. Not a big change from what we've been doing, but what if I have 5x squared equals 28? I can still get the squared thing by itself, but I get the squared thing by itself by divide instead of subtracting right here because I got a times 5. I can get rid of that by dividing, but it's going to leave a fraction thing. That's what I got to do. I got to get perfect square equals number, right? So I'm dividing by 5 to get that. X squared equals, it's a number, it's just a fractional number. I can apply the square root property here. I get square root of 28 over 5. So when we do simplifying radicals, in order to handle the solutions to these equations, we ought to do simplifying this kind of radical also because we do get fractions in there sometimes. Going to have to deal with that. Main thing about fractional stuff is you can still do them pieces separately because this is division in there, just like multiplication. That can be thought of separately. So we're going to think of that as the square root of 25 over the square root of 5, and we're going to ask our questions about these things separately. Is it a perfect square? Well, no, 28 is not a perfect square, and neither is 5. So that's my first question. Second question is there a perfect square factor? Not for 5, but there is for 28, right? 9 doesn't go into it, but 4 goes into it. So I can simplify this one a little bit using that. 4 times 7. I can't simplify this one, but this is just 2 right here. So this becomes plus or minus 2 square root of 7 over square root of 5. Now I'm going to think about my third question that I implied there would be for simplifying radicals. So we had the first question, is it a perfect square? If it is, then we can get rid of the radical. My second question here was, is there a perfect square factor? If there is, then I can shrink the radical, which I did on top here. Third question in this that I got to think about is there a radical in the denominator. Like usual with algebraic stuff, if we're going to write it out with a denominator, I want the denominator to be as simple as possible. I want to get a nice denominator to it. For fractions, we have to deal with the denominator. We want to get the denominator as nice as we can. I don't want an ugly number like the square root of 5 in the denominator, in the thing that I'm dividing by. So I can get around that here by rewriting this a little bit. It's called rationalizing the denominator. Maybe you've seen that already in the work, but I haven't done examples on here. If there's a radical in the denominator, we have to rationalize, which means I have to multiply top and bottom by something to get a nice number in the denominator. Simple kind of thing like just square root of 5 right here. The thing I would multiply them both by is another square root of 5, because that comes out to just 5 now. So now I can write this with a nice denominator. It's the same value, but I have a nice denominator on it now. Still plus or minus 7, square root of 7 times the square root of 5. I can put those together. It doesn't simplify anymore, but I have a nice denominator now. It's a fraction, it's just fifths, and that's the nicer way to write it. So that doesn't look a lot simpler, but it doesn't have the radical in the denominator. We got just one radical, and it's on top now. That's the nicer form on those things. No matter how I'm doing my calculation, it's easier to do divided by 5 than it is dividing by the square root of 5. So this is a nicer way to write things and calculate things. So that's usually the proper form. Those are the 3 steps to simplest radical form. Just going through those 3 questions. Mostly where we're going to see it is just on numbers. We did some with variables in there too, but when it's just on numbers, we use it to simplify these solutions to equations all the time. That's where we're going to see a bunch of that. Is it a perfect square? If so, we get a nice number out of it. We can get rid of the radical. Is there a perfect square factor? If there is, we can shrink the radical. And is there a radical in the denominator? If there is, we're supposed to rationalize it. The proper form for writing that would be with rationalizing the denominator. So let me get one a little bit worse here where we get some pieces put together, and I want to think about the actual numbers involved. So let me look at another perfect square equation like this. What if I have a number sitting here? No. That's not what I wanted to deal with. No, that would be an okay one, but that's not really what I want to deal with now. I want to know what happens if I have a fraction involved. So I'm going to go with something like, just put the number there. If I have a fraction there, I do have the squared thing by itself already. I'm already in the nice form. Perfect square thing equals number. So I'm ready to apply square root property. Square root of this, square root of this. I'm going to get the plus or minus in there. So I get x minus 4 equals plus or minus the square root of 80 over 3. I got rid of the squared. I got a radical now, but it's just on a number. I just want to write it in simplest radical form and solve for x. So solving for x is just doing a plus 4 on both sides, right? But how do you add 4 to plus or minus the square root of 80 over 3? They're not going to look, they're not going to look too nice, right? So it's really 4 plus the square root of 80 over 3, or 4 minus the square root of 80 over 3. I can't really put that together because one of them's just a number, and the other one's got this big radical thing on it. So I'm going to keep that separated. Those are my two solutions. I could get decimals from the calculator by punching that in, but I'm just going to write it in simplest radical form for my exact solutions. It's this, but I should simplify the radicals. So same three questions. Is it a perfect square? Well, 80 is not, and 3 is not. Nope. So I'm thinking the top and bottom separately. They're not perfect squares. Is there a perfect square factor? Not for 3, but there is for 80. Actually, 16 times 5 would work here. 16 times 5, that's my perfect square factor, so that's just a 4. I got x equals 4 plus 4 radical 5 over, that should have a square root on it. So square root of 3 in the denominator. Third question, is there a radical in the denominator? And there is. So I got to multiply top and bottom by another copy of it to get a nice denominator. That's how I get the rationalized denominator. Wrote that with a nice denominator. Square root of 3 times the square root of 3 is, of course, 3. Put those together into one radical, and you got your simplified form of that. The other number sets the same radical on it, so that's going to go through the same thing and just end up with a minus. That's the only difference there. So those are the two solutions in exact form. If I wanted decimals, I could get decimals out of it. Let me go ahead and get the approximate solutions on that one. Just to go through that process. So that first solution is 4 plus this 4 times the square root of 15 divided by 3. Is that 15 divided by 3, or is that the square root of 15 divided by 3? I got to be careful about that. So I'm going to put that in parentheses. Make sure I stop doing the square root then, and then divide that by 3. That should be the right operation. That's 9.16 approximately. And the other one, just a minus right there. I'm doing 4 minus that. A lot of the calculators, when you put that square root, the parentheses will come up automatically. That's a nice thing, because when you're dealing with a square root, you always got to know where the square root ends, and that parentheses is nice for that. That's the same thing with a minus. I got negative 1.16 approximately. Those are both supposed to be solutions to this thing up here. In that form, I could actually do a check in the original equation. I'm going to take a minute. I'm not going to wrap this up, but if I take a number like that and check it in the original, it should work out okay. X is approximately negative 1.16. Then I can square that negative. I can plug that in. Negative 1.16 minus 4. Square that. I get 26 point something. That is the same as 80 divided by 3. That should be the same on both sides. It's approximately the same. I need to make that visible. I did that calculation. I got 26 point something. 80 divided by 3 is 26 point something. I'm off by a little bit because it's a rounded, it's an approximate solution. But that came out. You can see it's going to be equal on both sides. We just have a rounding thing there. So those are the two. Those are the actual values to that. So we will do that kind of simplifying when we get that kind of answer, which is going to happen with our quadratic formula. And going to do a completing the square intro and lead it into the quadratic formula on Friday's video. So we'll see more of that then. Good having a little conversation going on here. We'll get more into that pattern and how it leads to a nice formula on Friday. Talk to you all then. Have a good day.